our next speaker for today is Lucas Ioan. He's telling us about here critical. No, go ahead.
Critical Ornstein-Zernike theory for planar random cluster model.
Thanks so much for the introduction.
Well, thank you everyone for attending, and thanks to the organizer for the invitation. The thing I want to talk about today is a joint project with Ioan Manolescu, who was my PhD advisor in Switzerland. And it, well, I will explain the title, which is not so clear in detail, but it regards the interplay between the subcritical and critical phases in the random cluster model in two dimensions. So I'm going first to explain what the model is. So it's a percolation model. So maybe not everyone of you are familiar with the percolation. So basically, percolation is a model of random. Sorry, can you see or yeah?
No, but on the camera. Yeah. For people online, it was not.
I will try to write large letters. Random cluster model is a model of percolation. So a model of random subgraphs of a lattice. And for this talk, we will choose ZD and even Z2 later on. But it's a model which could be defined on more general graphs. For now, I stick to ZD. And so I fix G a finite graph. For now. And I will choose randomly a subgraph of G according to the following probability measure. So the probability, I have two parameters, P and Q. And the probability of sampling a subgraph that I call omega will be equal to 1 over z, which is a factor that I'm going to explain the simplification later. P is the number of open edges of omega. 1 minus P to the number of closed edges in omega, that I call C. And I have an additional factor that is K of omega. So in this formula, K, so O of omega is the number of open edges in my subgraph. C of omega is the number of closed edges, which is just the total number of edges minus O of omega. And K of omega is the number of connected components of the graph. And also there is a detail that I'm going to explain, which is that I need to fix a pointing rule for the cluster that intersect the boundary. So for instance, say that my subgraph looks like this. So in white, so my G is like this finite box of ZD. The white edges are the open edges of my subgraph. Here I need to count the number of clusters. I need to specify a counting rule for the number of clusters that intersect the boundary. For instance, I could declare that in this configuration I have 4 distinct open components, but I could also make the arbitrary choice to wire all the edges of the boundary, and thus those two clusters would only count as one. And correction on this, for instance. Okay, so this gives me with two different counting rules. The one that I call the free one, in which this outer connection does not exist, and the one that I call the wire one, in which I count as one all the clusters that do intersect the boundary. So yeah. And sorry, yeah, I'll explain. So here, just let me mention that I could choose two different what I call boundary conditions, which is this counting rule. The wire I call it by 1, and the free I call it by 0. And the P and Q. So P is the parameter that belongs to 0, 1. It's somehow the probability of opening a vertex. If Q equals 1, sorry, then everything becomes independent, and I'm just retrieving the classical Bernoulli percolation model, in which I open an edge with probability P and close it with probability 1 minus P. This Q introduces a long range dependency. So P is between 0 and 1, and Q, a priori, is just a positive number. Okay?
P is the probability of opening the edge.
Yeah, exactly. But as you have this Q, the thing becomes a bit more complex because you have more dependence. But morally, is this yes? If Q is equal to 1, then it's really this concept. Okay. So far I have a finite graph, but it's classical that those measures they can be extended to infinite volume by taking G like an exhaustion of the infinite graph that I want to obtain. And in the case of the free and the wire boundary condition, it's known that those measures they would converge towards a so-called infinite volume curve. So as when GM goes to say ZD, then it is an easy monotonicity argument. Those measures they do converge towards the so-called infinite measure. And of course, here the choice of boundary conditions is important because it converges towards different measures, the wire and the flow. Okay. So, what are the important questions about this model? Well, plenty of them, of course. But the question that I will be particularly interested in today is the question of the behavior of the two-point correlation function. So for x belonging to ZD, what is the behavior of well, the probability under those 0,1 boundary conditions at parameter p and q that 0 is connected to the point x. Okay, so x is a point of ZD, and I'm interested in the probability, that 0 and x belong to the same cluster. So for instance, if there exists an infinite cluster, then this would be lower bounded by an absolute constant. If there exists no such cluster, this would decay as x goes to infinity. And one of the important features of the model is that well, it exhibits a phase transition. So for now, I'm sticking to the planar case. So now d equal to. So we consider the graph as, and I'm going to try and sketch all the known results in only one drawing. So it will the first time that I do this. Maybe it's not going to be so good, but at least I try. So here are the values of p and q. So this is going to be the value of p, and this is going to be the value of q. So first, there are some interesting points. So as I said, q equals 1 is an interesting point. And there is also a relevant point, which is p is equal to 4. And by the way, for the physicists or maybe the people that know more about spin systems, this quantity is really related to spin-spin correlation in, say, the Potts model or the Ising model for those who know. When q equals 2, this is exactly the two-point correlation function of the Ising model. And when q is an integer, this corresponds to the two-point correlation function of the q Potts model. So it's really of physical relevance. This object is really of physical relevance. So here in this zone, I will not be interested in because nothing is known. Nothing. I'm sorry. So not even the existence of a phase transition. And this I can discuss later, but it's because in this region we don't have any correlation inequality, which is basically the basic tool for starting to work with this model. And there exists like a critical line, which is explicit in 2 dimensions, which is something like this. Oh, I should have plotted. Sorry, I should have plotted Q and P. Well, I left it there. I'm sorry. I will put P here and Q here. It will be more simple. So in this zone, nothing is known. Q equals 1. Here is Q equals 4. And I have a critical line that starts at 1/2 that does something like this. And it's explicit. So PC of Q is equal to square root of Q divided by 1 plus square root of Q. Okay. So below this line, when P is small, the behavior of the model is called subcritical, which means that basically I don't have any infinite, there is no infinite clusters, and the correlation decay very fast. I will give more detail after, but this is the subcritical region.
Fast you mean exponential?
Yeah, exponential, but I will go towards the subcriticality. Here is the opposite, supercritical, so I have a unique infinite cluster. And basically, the graph is very well connected with very small holes. And here, the behavior is way more interesting because it's a critical line, and I have two different phases. Either Q is between 1 and 4, either Q is larger than 4. So in the zone Q is between 1 and 4, we call it the continuous critical. I will explain. And here the discontinuous critical.
So in the supercritical region,
Yes.
you still have what extra or not?
No, actually, since there is a unique infinite cluster, the probability of the 2.0 x being in the infinite cluster is always lower bounded by, say, an absolute constant. So there is a positive probability to be in the same infinite cluster, so to be connected.
So it's
so the 2-point function is lower bounded by an absolute constant that does not depend on x.
yeah, so it's like there is a region where there is kind of no symmetry breaking, and then there is a region where above the supercritical it's symmetry breaking.
The supercritical region is the symmetry breaking, and it means that basically you have long range order.
Fantastic. Okay, that is what that's
exactly
work. Okay,
so it means, for instance, that if you take anything with flat boundary condition, then you are in the zone in which the implicit probability of the larger probability of two speeds up.
And of course, that is the power law behavior between 1 and 4.
On the critical line, this is, so I will explain, but on the continuous critical, this is the power law behavior, so the classical QFT business. And on the discontinuous critical line, it's a bit weird. You have a first order, a first order phase transition, and you have actually different Gibbs measures. So
there are like power law behavior, but with complex exponents or something.
This I don't really know, but what I can say is that in the free measure, you look subcritical, but in the wire measure, you look supercritical, and those are not the same. So you don't have this power law behavior.
Okay.
Okay. I will sum up what I just said in a list of results. So let me do I will try to do a synthetic presentation. So I have like 4 different regimes: the supercritical, subcritical, continuous critical, discontinuous critical, and I can ask some questions. Here question: are phi0 equal, is phi0 equal to phi1? If this is the case, basically you have a unique use measure because they are all sandwiched in between those two that are maximal and minimal. So do you have this decay of 2 points? Now maybe I can say infinite cluster and decay of 2 points. Question mark, and here I have the very big. They're gonna so high because it's gonna be full at. So here are the answers. In the supercritical regime, we have indeed those 2 measures that are equal. So unique Gibbs measure. Basically, the picture is almost totally empty. There is no infinite cluster, and the decay of the 2-point function is actually exponential. And the exponential in the distance. So the probability that 0 is connected to x, it decays as an exponential in the normal, let's say. In the continuous critical case, so p equals pc, this specific value, and q is between 1 and 4. Then there is also a unique Gibbs measure. There is no infinite cluster, but this time the decay of the 2-point function is algebraic or polynomial. So this hints at a conformal invariant scaling limit. This continuous critical, it's a bit weird because it's the only case in which you don't have the equality of those Gibbs measure, and you have an infinite cluster, yes, in the wire, but in one measure, and no in the free. And the decay of the two-point function depends on the measure, of course, and there is no decay. No decay in the wire, and exponential in the free. In the zeros. And for the supercritical measure, you still have equality of those Gibbs measure. You have a unique infinite cluster, and the decay of the two-point function is you have no decay. So it's what I explained. You have this long-range order or symmetry breaking, and this does not decay at all. It's lower bounded by an absolute constant.
Sorry, and the
Yes.
point Q equal 4, PC equal 2/3, where should we find it?
It's included in the continuous critical, but it's somehow special in some regards, but still on the continuous critical line. So at this point, you have a unique Gibbs measure, and you are on the second line.
By algebra, you mean polynomial?
Polynomial, yes. And well, I can't really name all the people that prove this, like led to this array because it's a large number of works. But today I want to focus on what happens to the decay of the two-point function when you switch to exponential to algebraic. So when p increases to pc, and you have in the regime q is between 1 and 4. Because somehow, this transition is continuous, you should expect to have like a formula that sort of interpolates in between this subcritical regime and this critical regime. And that's what I'm going to focus on the top. I'm kind of happy with this, it's very visual. Okay, so are there any questions on this stage or may I go ahead? Okay, so now I want to specify a bit those two regions of the array. And I'm going to start writing theorems. The first theorem that is important is the following. And it comes back to Vincent Beffara and Hugo Duménil-Copin. And it was called in 2012. So remember, all of this is known for d equals 2. But d equals 2 is very special.
Yes. Just like perhaps a spoiler question, but indeed, so here, like as a poor physicist, I would compute the twin function, and I would then express the correlation length. I need like an analytic form of the correlation length so that the exponential can interpolate.
Yeah.
But then I guess for that you have to solve exactly the model.
Yeah, exactly. So when I say explicit, it's not really explicit because it will be a formula involving the correlation length, which I do not compute because it's hypothetically polynomial in PC minus p. So this, it stays under the form, well, psi of p or whatever later in choose. But then I want a formula that interpolates thanks to this quantity between the subcritical and the continuous critical. But you'll see there is a correction to the subcritical to the exponential decay, and that's the term I'm interested in. So it won't be more explicit than exponential n over psi.
That's fine.
No, but I want to explain. Yeah, it's fine. It's not that explicit, but I will explain. So here is the theorem. So it's the existence of the correlation length. For any, so here Q is fixed. So for any Q larger than 1, for any P smaller than Pc, and for any X. So here it's convenient to parameterize the point I want to reach by its direction on the unit circle, and then I just blow it up by a constant. There exists the so-called correlation length, so psi P of X, which is a positive number, positive, very positive, such that the two-point function behaves like this, and the probability that 0 is connected to nx, well, here nx might not be a point of the lattice that I don't care, just choose the closest. I just don't want to put this floor function at an anymore. So I'm doing this. It's equal to when exponential minus n over psi of x times the 1 plus ln. So this is just what you said. This is like the theorem stating the existence of the correlation length. This is not difficult to prove when P is much smaller than PC, but you need a lot of work to push it all the way up to PC. So this was the first achievement of Lefara and Zernike. But actually, we can, so this quantifies somehow the exponential. This is the quantity that pulls, that leads the exponential decay of the two-point function. But actually, we can go one step further and try to compute this two-point correlation function at a level of precision that's better than just exponential of little of n, which is not so good. So there is an improvement of this, which is the second theorem, which is called the Ornstein-Zernike theorem. And it goes back to Campanino, Biofé, and Rémy. And it was proved in 2008, and is the following. So for any Q in the same setting, so for any Q larger than 1, P smaller than PC, and there exists I'll say X in the unit circle, there exists a function psi of P such that, and I'm going to, I want to put it in the default platform. Yeah, I can do it. So the probability of connecting 0 to nx, and I'm sorry, from the beginning, I'm omitting the boundary condition because I'm in a subcritical regime, so I have only one gives measure, and I'm also omitting the parameters P and Q. They are obviously, it depends obviously on P and on Q, such that this is equal to, well, I have my term exponential n over psi, but I have a polynomial correction, and this polynomial correction is psi t of x divided by square root of n. And this is very precise because it's up to 1 plus ln of 1. So this is much more precise than this. This result is much more precise than this because it quantifies somehow the polynomial correction that I have to add to the two-point function so that it decays really like a pure exponential. And you, yes?
Does your correlation length really depends on x when n starts?
Not really. What you can prove is that it does depend on x because you're in the subcritical regime, so you should fill the lattice. So it won't be a constant function of x. But on the other hand, you can prove that, for instance, the function x that maps x to psi of x is analytic in x or this type of results. This you can prove. But it still depends. Well, it takes its value in a compact interval, but it still really depends on x because the model is not isotropic, so it really fills the lattice. Obviously, when you approach the critical points, this should become rotational invariant because rotation is a conformal symmetry. So so you might be able to prove that when you rescale it by the equation of the circle, this should converge to a constant. But it blows up, so you should divide by the rate of blowing up, and then this converges towards something that does not depend on it. Okay, and if you are still alive at this stage, you will ask me why this is earlier than this. Which is a legit question, and it's because this theorem was actually proved under the assumption of exponential decay of the two-point function. So the correct result would be if this decays exponentially, then it decays like this. But of course, pushing up all the way to the critical point, it requires some work, and the work is going to happen. So no logical flow. Okay. And now the question that I'm interested today.
And the techniques are probably completely different.
The techniques are quite different, yes, but I'm going to focus on the second one, so I will explain more in detail how you prove such a test.
And this is for
This is for that. So Actually, it's a very good question because actually it's not for those two theorems that are true for any d, but it's significantly much difficult. So this theorem was generalized to any d by Giannini, Copin, Raufi, and Tassion in 2017. It's a huge and very important work. It's called the sharpness, the fact that just below the critical point then you decay exponentially. So it's really like a beautiful piece of work. And this theorem, well, it extends to any dimension, but here you should replace the square root of n by n to the. Well, there is an exponent that depends on the dimension, and it's d minus 1 over 2. No, I did not mess up. Yes. Well, minus, because I put it in the right. If it's d minus 1 over 2, so 2. So if d equals 2, it's 1 over 2, and it should, no, it's good. Sorry. How about this? I'm very bad with numbers. Okay. And the last theorem maybe that I want to mention before I'm going to the result is the following. So theorem, which is again Beffara and Giannini, Copin in the same article. So it's 12. They also prove that when Q is between 1 and 4, then the probability that 0 is connected to the boundary of the box of size n. So this is my notation for the box of size n, and this is the boundary of the box. It's lower bounded by n to some alpha, and it's upper bounded by the opposite, lower bounded by n to the minus 1, and upper bounded by n to the minus alpha for some value of alpha. So it really means that now the correlation function can't decay exponentially. The two-point correlation function can't decay exponentially. If it was the case, then we would sum over the boundary, it's a polynomial number of points on the boundary, it would still decay exponentially.
This is for any dimension.
This is for the critical point. That's what you meant?
Or the dimension d.
This is PC of Q, and this is for d equals 2.
But can you repeat your last statement about so in a sense of this implies what about the
I mean, this estimate implies that the two-point correlation function, so the one in which you replace just this boundary by an x by a given point, it can't decay exponentially, because if it were the case, then you just sum this estimate over all the points on the boundary of the box, and this you would sum a polynomial in n times exponential minus n, so it would still decay like an exponential. So you could not have this. So
the rho is the lower bound.
The importance is the lower bound. Okay. And the upper bound gives you that you don't have an infinite cluster, so you're really in the constant critical region. And obviously, this is exactly at the critical point, right? This is a critical behavior, sorry. And well, the goal of, I mean, one of the important endeavors of the percolation theory is to prove that this estimate is still valid in other dimensions. But this is very difficult. I think you probably would be very famous if you would prove it. Okay. So now the question that I'm interested in still, it's how do you switch from this behavior to this behavior? And now I can finally state my results. Yeah, so after half an hour, so it's not bad. For the result. So for the result, I need to introduce another quantity, but it's a technical thing. It's the so-called one-arm connection probability. So I'm calling pi 1 of R, which is equal by definition to the probability at PC and Q, okay? And here Q will be taken between 1 and 4, so I don't need to specify which measure I'm considering. That 0 is connected to the boundary of the box of size R. Okay, so this is the definition. It's the so-called one-arm connection probability. And now the theorem is the following. 。 So another school. And it will hopefully be a paper soon. So the theorem is the following. So for any x, for any q between 1 and 4, but 4 is now excluded, and I'm going to explain why. For any x in S1, it is the case that the probability that, and sorry, for any p smaller than c, it is the case that the probability that 0 is connected to an x is asymptotically equivalent, so I'm going to explain this term later, to exponential minus n over psi, sorry, to pi 1 of psi of p squared. So in my notation, it was this square times sorry, square root of psi over n times exponential minus n over psi. So I'm going to explain. So first, by asymptotically equivalent, I mean that it's lower bounded and upper bounded by this quantity times two different constants, but those constants that do not depend obviously neither on p, neither on x, neither on n, so it's really absolute constants. And well, if you look at this formula, it's pretty similar to this. It looks that we actually kind of computed what is the quantity psi p. What is new in this formula is that this is uniform over p. So here, yes, if here this function depends on p and it can blow up, and we kind of replace this by a constant. Okay. So what I mean is that this formula is valid simultaneously for all values of p, right? So it means that in this formula you could take double limits, say as n go to infinity and p go to p jointly, and see what happens in this formula, right? While in this you couldn't, or you need to understand what is. Okay. And now
Do you also have a closed formula for pi 1? What?
now pi 1 it should be polynomial in R at the critical, so it should be R to the 1 arm exponent. So this should be hypothetically it should be R to the minus alpha 1, right? But this is open. We don't even know that, I mean, as mathematician, we don't even know that the random cluster is a planar random cluster is conformally invariant. This problem we can't prove. We only know it for easing, so Q equals 2. And we also know it for percolation, but in the triangular lattice. So very specific case.
Sorry, can I ask something?
Yeah.
If P is, if I understand correctly,
Yeah.
if P is PC,
Yeah.
Psi goes to infinity, right?
Yes. So if P is PC, this formula doesn't even make sense because psi is infinite.
But there is infinity, that's one, right? It's just
This, yeah.
right? But is the other part convergent to something?
It does not really make sense because pi 1 of infinity should be 0. So here you have something that blows up, and here you have something that go to 0. But yes, what this formula suggests, those things should compensate.
This should be given like a polynomial.
Yeah, and it's actually the case. So in a very recent paper, Ioan Manolescu and Ioan Manolescu, they proved like the scaling relations for the planar random cluster model, and it gives you some relation between the critical exponent. And in particular, I guess, I mean, I can't really work out this one, but I think this formula is compatible with this scaling relation. Mm-hmm. So this gives you, I think this would give you a scaling relation of this type. Yeah, it's correct. One half times the exponent of psi will compensate this exactly. And yeah, so just to finish, and then I will briefly talk about the proof. What's interesting in this formula is that if you look at this term, it's really a subcritical term. So it looks at this like this one, right? So it means that when I take n much larger than the correlation length, which means that basically I'm looking at a very subcritical system, then I would have a decay which is like the typical Ornstein-Zernike decay that was predicted, proved in this formula. But now what's interesting is that if I take n of the order of the correlation length, then this term is not really significant anymore because it is bounded, and this term takes over. And this term is actually what you would see in the critical random cluster model. So you can prove that at criticality, the probability that 2 points are connected is of this order, maybe pi1 squared. It's something that is really, you really have an interplay between this term, which is a critical one. It's computed at PC, not at P. Still it depends on P because you have a P here, but it's like by essence a critical term. Well, this is a subcritical term and they play together. So you could take, for instance, joint limit in which n over psi remains bounded and see what happens. Okay? So I think if you have questions, it's a good moment to ask. Sorry. Yes.
Can you explain the meaning of the asymptotic?
Sorry. Yes. So I'm just saying that if I call, if I call the right hand side, I call it f of n, p, and x, then the claim is that there exists c minus c plus positive, such that well, c minus times f n p x is smaller than the probability of connection, which is smaller than well, the same thing with c plus and x. For any n p x, which will be lower and lower than the dimension. Okay. Okay, so now I can explain briefly the proof. It's a bit like when the nightmare begins. So the idea is not so complicated, but the details are, as always, I guess. So the idea is to explore the so here I have a point which is 0, like a specified point, and the idea is to actually slice it into hyperplanes. Like this, and so on. And these hyperplanes, they are spaced by the correlation length. So here the x does not really make any difference because, as I said earlier, we would just change it by a constant, but it's not something that matters. So maybe I fix a vector and I call psi p the psi p of this vector. I want to keep things simple. Okay. It's okay. So those hyperplanes, they are not like I drew them orthogonal to the unit vector, but they could be of any angle. And now what I'm going to do is that I'm exploring the cluster of 0. So maybe my exploration does something like this, then like this, and eventually it goes back to itself, for instance. And then I'm just keeping track of the position of the first intersection of my exploration with the given hyperplane. Or maybe not the first, but the highest most. Any choice would give you the same list. Okay. And then, so this is my xy. This is what I call xy. This is what I call x2, x3, etc. And then I declare that x4 equals x5 equals blah, blah, blah. And they are dead. So my exploration is like this. Okay. And now the idea is to understand what are the properties in a suggestive process of this process xk. Of course, you would like to say that it's a random walk, but it's really not a random walk because you have spatial dependencies in the random cluster model that maybe make the analysis difficult. But actually, what we do is that we prove that it should be a killer random walk. But what we do is that we prove that it's almost a killer random walk in the sense that you can enlarge the probability space and find some points and find a renewal process. Like a sequence of random points such that the process x1 t1 is what we call a killed Markov renewal process. So that means that I have a renewal process, just a sum of independent positive random variable. Those are my t1s, t2, etc. And on top of this, if I only track those increments, so they have a random length that is indexed by the renewal process, this corresponds to a random walk, like this. Okay. And of course, it has a chance to die at any step. But what really matters is that since we choose the scale accurately, which is this side, it has a positive chance to die. I mean, this process is roughly independent of the choice of. It would be always the same for any circuit. Okay. So now let me maybe state what I mean by this. So yeah, the definitions are not really convenient, but you should really keep in mind that this is just a random walk on top of a renewal process. So you have this renewal process, you put a random walk above it, and this is basically the process that you are going to study. So definition, a kill renewal Markov process. Markov process. Sometimes it's also called a compound Markov process, which shows the lengthy name, is xk decay such that so the first requirement is that if tk is dead at some stage, then x sub tk will be dead, and so will be for the next steps. And then conditionally on everything that happens before tk, the times tk, so conditionally on all these events, and the fact that xtk is not dead at the stage k, then x t plus tk minus xtk, and the further steps of the renewal process, so tk plus t, as a process is independent of has a fixed law. It's a very weird way of writing a Markov property, but it's basically a Markov property. Condition on what happens before the time tk, when you have really a decoupling thing that says that the next steps are independent of what you solve. And well, the theorem is that
Yeah, that's equivalent of saying that k does not depend on k minus 2, another k minus 1.
And that's equivalent basically to saying that once you explore everything that happens before tk, you know that you are at a renewal point, and the future of the process is totally independent of what you explore. So it's a very weird way of phrasing it, but that's this. It's really like a random walk type behavior. But now the theorem is the following. You can enlarge the point space. There exists a coupling say x tk such that so when the process x k divided by xi, you also need to rescale the steps, the size of the steps by xi. LT is a renewal Markov process, and with exponential tails. And those tails, they are independent of t. Sorry. It means that whatever the p I choose, the renewal process that I get is always the same. Actually, it's a bit of an overstatement. It's not really independent, but we prove that, say, the killing rate or those type of quantities, they are uniformly bounded as a function of p. So they might move a little bit, but they will not blow up or go to zero when p goes to peace. So this is the first theorem. And the second one is that one remains valid. Yes.
Just because
Yeah.
What is the exponential case of the process?
It's exponential case for both x and t. So it means that the interrenewals, they are very quickly. You have an exponential case that for t2 minus t1 or t plus 1 minus tk, and also for xtk over xi minus xtk minus 1 over xi. So you have both exponential case for this quantity, but also for the increments of the process.
But it doesn't depend on P for P smaller than PC or NP. So what is P? Yeah, P.
P is the probability. P is the P of the order plus 1. So the point is that
Is it the same P as before? The P smaller than PC?
Yeah.
But this is only valid for P smaller than PC.
Yes. Sorry.
Okay.
But no, my bad.
Okay.
I'm always working for this.
Yeah.
Yeah. But the point is that the killing rate, so say for instance the probability of dying at any point, if you fix the scale and it does not depend on p, if you do not make this choice of psi p here, you choose say 10, of course the killing rate will depend on p. Because when you overcome when you are larger, when p is trivial such that the correlation net is much larger than the psi, then this would grow more and more and more. So you really need to choose a dynamic scale that depends on p to have something that is uniform over p. That's the point of independent of p here.
Xk is xtk.
Yes, it does not really matter, but it's. I mean, in my definition, it should be xk, which is already works. I mean, it's just a matter of writing the definition. And the second important bit is that so the conclusion of the first bit, it remains valid under the conditioning. And this is very important. That xn does not die. So it means that if I choose a point that is very far away, that is my n, and then I condition my process on not dying, so on surviving until it hits n, well, I won't have a killed Markov renewal process because it's not killed. It needs to survive until time n. But what I mean by one remains valid is that the exponential this process still have exponential test. It's this that remains valid. And this, if you think about it, it's not so obvious because imagine that you have a kill renewal process, and now it wants to survive up to some time. It could do it by making only one very large step. Okay, this could happen. Or it could also survive. It's a sort of large deviation scenario. It could also survive by asking to survive for any and still have small steps and asking for survival for this small step. But you have a competition in between two scenarios that actually are closer together. But the important thing is that we are able to prove that if you condition to reaching n, then the distribution of the interrenewals is stabilized towards a given distribution that does not depend on n. So this is important. It's a bit subtle, but it really means that you survive by not having a very atypical behavior, but just changing a little bit the distribution of your interrenewal and your the steps of the process. And what I want to conclude, maybe it's time to stop. At which time did I start? I have a little bit of time. So now, how do we prove the main theorem? Well, I just want to say that now that we have this, property, the probability of reaching a given point is really like it's a result about kill Markov processes, like kill renewal Markov processes. So it's really like when I study the probability that 0 is connected to n, it's a bit as if I was studying. Of course, there are some details. The probability that my kill Markov renewal process 1 survives up to time n, and 2 hits exactly the point that I want to. And this is the meaning of the Ornstein-Zernike formula. So if you remember, you have this n over psi times, say, square root of psi divided by n. This term, it corresponds to the probability that you survive at any steps. So basically, you have n over psi steps. You need to pay a constant price for each one of those, which costs you this quantity. And now given that you survived, the probability of hitting a given point along this hyperplane, it should be given to you by a local limit theorem, or like a central limit theorem. And that's why this n over psi, square root of psi over n, sorry, enters the picture. It really comes from a local limit theorem. It's not a local limit theorem in 2D, but in 1D, because you lose one dimension. Like one dimension of the space is used as the time reference, so you really have this d minus 1 over 2. And now I still need to explain the.
And the one you that equals 2.
Sorry?
Was you that equals 2.
If all the dimensions would play the same role, then I would have zeros. But here I lose one dimension because one is used for the time, so it's d minus 1 over 2. So the d goes to d minus 1. I lose the orthogonal dimensions. And now I still need to explain two things basically. I didn't explain anything so far, but I need to explain where does the pi1 square come from. But this is a bit complicated, but yes, maybe I won't go into this. I mean, when you reach say x2, you can prove that your cluster is kind of well opened. It has the size of a few correlation length, so it's not difficult to go from there to there. This is like the so-called RSW theory. It says that at the scale of the correlation length, this connection, it really will be a constant. But when you start from 0, it's different because you start from a given point, right? So this connection is more costly. The one in which you want to reach the first hyperplane, this costs you more. So that's the first pi1, and then the last pi1 is when you want to reach the hyperplane. So you have this special term, which is not so important actually. What is important is really to have a n over psi and n over psi here. And yes, maybe for the end of the talk, I want to explain why the result is restricted to q between 1 and 4. And the reason is the following. So on the way of proving this result, we also prove that somehow the typical opening of a cluster that connects 0 to n is of a size a few correlation length. So here, when I made this drawing, this arc here, it should really be of order of some psi of p, maybe 10 psi of p or something. But the thing that we proved is that the width, sorry, maybe I'm stopping with all the colors, but the width of the cluster as a function of p, the typical width divided by psi of p, it remains bounded. So it's bounded. It's close to 1. And it should not be the case when q is larger than 4. So this is something that is really interesting and has not been proved yet. So maybe it's an open question. Or interesting problem. But don't work on it because it will be proved soon. It's not a very good way of selling the problem. But it's when q is smaller than 4, strictly smaller than 4, the typical picture for a long cluster is this. And here it has fluctuation that are of order square root of n over psi. Psi t. So this is like the fluctuation. It fluctuates like a random walk. And the width of the cluster is of order a few psi. But it's of order psi, so it remains bounded. It does not depend on n. Now, when q is equal to 4, so this is the most difficult case. So this is truly open. So this you can work on it. I would expect, it's also a conjecture by myself, so maybe you shouldn't work on it because it might not be true. I don't know. I would expect that it's almost the case So you still have a square root of n fluctuation. But now for this, you should have logarithmic correction, I think. It should be something like log n times psi. This I won't prove, it's not a statement. And when q is larger than 4, there is something really interesting that happens, and it's called the weighting phenomenon. So actually, this cluster it becomes really thick. So it would become like this. It would still fluctuate like square root of n, divided by psi, sorry. But also the distance between the upper and the lower interface should be of the same order. It should be also of order square root of n over psi. And basically, the reason for this is the following, and I will stop, I promise. The reason for this is the following. As you have two different Gibbs measures, you have the free one and the wired one. When you explore locally, like the region between those two interfaces, what you see is a wire arc on top and wire arc on bottom. So it's free for you to fill the region with a wire with a big cluster. And so you have a phenomenon that is called entropic repulsion that says that if you have this liberty, this freedom to fill all the gaps in between your cluster, it costs you basically nothing to fill this region, then they would repulse and act like two independent fundamentals. Here you see you're really subcritical, so it's not free for you to fill this region. So it's much less costly for the two interfaces to stick together in this regime in which Q is larger than 4. It's really free to fill all the void in between those two interfaces, so they will really repulse each other. And yeah, I'm stopping here.
We still have some time for questions, if there are some.
Why Ornstein-Zernike?
Is the name of two physicists, Ornstein and Zernike, as you might know. Yes, and actually they predicted the formula with the polynomial correction to the exponential decay, and it's very old. It comes back from I think very beginning of 20th century. And they predicted this because they had made an observation with an experiment that was showing this anomalous, and at this time it was anomalous, but they thought that it was pure exponential decay. And then they made some computation and then figured out that it was not really pure exponential and that there was this polynomial factor. And then they made a computation, which is totally wrong. I've read it, but they made a computation and somehow miraculously it's the good factor. And then it was proved later on by other people. But it stays Ornstein-Zernike prediction.
I have a memory of this by the thing done by Ioan Manolescu.
Yes, exactly. So the Ornstein-Zernike theorem is really the rigorous proof of it. It really comes back to Ioan and Manolescu. Those are the people that really proved it rigorous. There were earlier works, but they were really perturbative. So when P is very, very small, but they were the ones to shift to the piece or to the regime of exponential decay. But yes, all the stories you're familiar. Yeah.
And explain how you choose your TK. Maybe you saying that I totally missed that.
Oh, I choose
TK.
So I don't choose it actually. So what we prove is that there exists an abstract coupling such that this property holds. And actually, I can tell a bit more because those TK, they are not chosen really randomly. They correspond to the times at which the cluster really is opened. So you see, I'm exploring the whole cluster time by time, like this, slice by slice. And when the width of it is not too big but not too small, like really a few psi of p, maybe one psi of p, then I can work out a mixing argument and really say that with a positive probability, the rest of the future will be sampled uniformly from its past. So it's those really you have the renewal properties.
This is sort of the typical length of your.
Yeah, exactly. So the typical length of the cluster is of order maybe a random variable times psi, and I choose my t when this random variable is equal to 1. And I prove that this happens exponentially often, which somehow gives me this. But there is also I cheated a bit because there is another difficulty, but basically those T correspond to the times in which the cluster is not too much open, but not too much closed. So really regular. Yeah.
Well, we thank again our speaker. Yes, we see in a week. There is well, as I said, you can find all our program can be found there. I guess it's really easy this time at the lesson.
The big team in the